The universe, vast and enigmatic, has long been a subject of human curiosity and wonder. From the earliest stargazers to modern astrophysicists, the cosmos has inspired countless theories about its origins, its nature, and ultimately, its fate. Among the many hypotheses about how the universe might end, one of the most compelling and widely discussed is the theory of the Big Freeze. This concept, also known as the heat death of the universe, presents a future where the cosmos continues to expand indefinitely, leading to a cold and desolate end. To understand the Big Freeze, it's essential to first consider the current state of the universe and its expansion. The universe began approximately 13.8 billion years ago with the Big Bang, a colossal explosion that set everything into motion. Since then, the universe has been expanding, with galaxies moving away from each other at incredible speeds. This expansion was first observed by Edwin Hubble in the 1920s, and it has since been confirmed by numerous observations, including the cosmic microwave background radiation, a faint glow left over from the early universe. The Big Freeze is predicated on the idea that this expansion will continue indefinitely, unlike other theories such as the Big Crunch, where the universe might eventually collapse back in on itself, or the Big Rip, where the fabric of space-time might tear apart. The Big Freeze envisions a universe that grows ever larger and ever colder. This relentless expansion is driven by a mysterious force known as dark energy, which makes up about 68% of the universe's total energy content. Dark energy is thought to be responsible for the accelerated expansion of the universe, pushing galaxies further apart at an increasing rate. As the universe expands, the distances between galaxies will grow, and the light from distant stars and galaxies will become increasingly redshifted, eventually fading from view. This redshift occurs because the wavelengths of light are stretched as space itself expands, shifting them towards the red end of the spectrum. Over time, galaxies will drift so far apart that they will no longer be visible to each other, leaving each galaxy isolated in a vast and empty expanse of space. The night sky, once filled with countless stars, will become dark and barren. Within galaxies, the stars themselves will undergo significant changes. Stars are the engines of the cosmos, fusing hydrogen and helium into heavier elements and radiating energy into space. However, stars have finite lifespans. Small stars, like red dwarfs, can burn for trillions of years, but even they will eventually exhaust their nuclear fuel. Larger stars will end their lives more dramatically, exploding as supernovae and leaving behind neutron stars or black holes. In the far future, as the universe continues to expand and cool, star formation will slow and ultimately cease. The remaining stars will burn out, leaving behind white dwarfs, neutron stars, and black holes. As the universe approaches the Big Freeze, the temperature will continue to drop. Currently, the average temperature of the universe, as measured by the cosmic microwave background radiation, is about 2.7 Kelvin, just above absolute zero. As the universe expands, this temperature will decrease further, approaching absolute zero. In such a cold environment, the processes that sustain life as we know it will become impossible. Molecules will lose their energy, and chemical reactions will grind to a halt. In this distant future, black holes will dominate the universe. These enigmatic objects, formed from the remnants of massive stars, have gravitational fields so strong that not even light can escape them. Over incredibly long timescales, black holes will slowly evaporate through a process known as Hawking radiation, named after the physicist Stephen Hawking, who first proposed it. This radiation causes black holes to lose mass and energy, eventually leading them to shrink and disappear. As the last black holes vanish, the universe will be left with a thin soup of particles, primarily photons and neutrinos, spread across an ever-expanding void. The Big Freeze represents a universe in its final stages, characterized by maximum entropy. Entropy, a measure of disorder, tends to increase over time according to the second law of thermodynamics. In the early universe, there were regions of low entropy, where matter was clumped together to form stars, galaxies, and planets. In the Big Freeze scenario, the universe reaches a state of thermodynamic equilibrium, where no further work can be extracted from energy sources, and everything is evenly distributed. This state is sometimes referred to as the heat death of the universe, a somewhat ironic term given the cold and desolate conditions. Despite its seemingly bleak outlook, the Big Freeze is a testament to the incredible forces and processes that have shaped the universe. It underscores the impermanence of cosmic structures and the relentless march of time. Yet, it also invites reflection on the nature of existence and the role of humanity within the cosmos. In contemplating the end of the universe, we are reminded of its beginning and the intricate tapestry of events that have led to the present moment. The Big Freeze also raises profound philosophical and existential questions. What does it mean for life, consciousness, and meaning if the universe is destined to end in such a manner? Some might find solace in the notion that the universe's end is so far removed from our current experience that it bears little relevance to our daily lives. Others might see it as a call to cherish the fleeting beauty of the cosmos and the opportunities it presents. In considering the Big Freeze, one must also acknowledge the limitations of our current understanding. The nature of dark energy, the ultimate fate of black holes, and the potential for new physics beyond our current models are all areas of active research and speculation. As our knowledge of the universe expands, so too might our understanding of its ultimate fate. The Big Freeze is but one possible outcome, and the universe may yet hold surprises that could alter its trajectory. In the end, the Big Freeze is a reminder of the universe's vastness, complexity, and mystery. It challenges us to explore, to question, and to seek understanding in the face of the unknown. It invites us to marvel at the cosmos and to ponder our place within it, knowing that while the universe may one day grow cold and dark, the light of curiosity and inquiry will continue to burn brightly in the human spirit.